Hi, this is Matt York, and I am going over part three, or no, not part three, exam three, part B, one and two, for Dr. Ko's Transport 2 class. So actually at this point, I'm going to solve a couple of different differentials. Um, and first I'm going to start explaining this problem, and then I'll go one by one each differential that we're going to be solving. So first off, the problem at hand is a closed cooling tower, and in this cooling tower, it's actually stuffed, um, and this stuffed area will be represented as A. It's a specific area in meters squared per meters cubed, while the whole tube, the whole cross-sectional area of the tube will be represented by um, large A in meters squared. So in this cooling tube, we have liquid water flowing down at a flow rate of L in kilograms per meter squared per second, representing the liquid flow rate. And we have gas flowing, so liquids flowing downwards and gases flowing upwards at a gas flow rate of G in kilograms per meter second squared. And so we're going to do all these differentials in respect to position. So we need to define a position in this cooling tube. So we have the top, I'm just gonna call like top Z equals 0. That's just, I can pick that position as anywhere as long as we go in respect to that position. So we're gonna call the top Z equals 0, and actually we're going to have the position increase downwards through this tube. And that will come in handy later, but it is important to know that the position does increase when going downwards. So anyway, to start off, we are going to look at, or not look at, we're going to solve the differential for the molar gas concentration, molar gas concentration in respect to position. So to start off with that, and I'm gonna have to move this around a little bit because sorry, I don't have a good space for this camera today. But to start off with that, I'm going to look at the things that are changing in respect to the gas concentration in this tube. So first off, I know that the, well, obviously the molar concentration is changing, but also the liquid flow rate of the gas is changing. Well, I want to get this within, or in terms of meters per, not meters, moles per second. And if I want to get in terms of moles per second, I need to multiply this Gy by the cross-sectional area divided by the molecular weight. So that's going to be our left side of this equation. And on the right side, we're going to see, okay, how is this concentration, this molar concentration even changing? Well, in order for it to change, we know we need the mass transfer coefficient, and that's going to be multiplied by the concentration of the liquid, and because we have a concentration of liquid, and that's, or we have a concentration of the liquid and a concentration of the gas. So in order for this gas component to change, we need to find the difference between the liquid and the gas concentration multiplied by the mass transfer mass transfer coefficient, and then also multiplied by, since we're going through this whole tube, the specific area of the stuffed part of this tube and the cross-sectional area of this entire tube, it's going through all of it in respects to position. So before I move on, I do want to simplify part of this for us. So we're going to use this part of the equation a lot here. And I don't want to write that out every time. So we also know this, as we have earlier in our class. This is also defined as the molecular, or no, not molecular, the molar flux of the water here. So we're just going to define that as the molar flux of the water. So instead of writing this out again, I could write Kc equals the concentration of liquid minus the concentration of gas, but I'm just going to write as the molar flux of water, and I'm going to put this in terms, like just we did in part A several times, in terms of pressure. So we're going to put this in terms of the pressure at the saturation point, as we just did in part 2 of the first part of this exam on A. And we're going, in order to do that, in order to get us in terms of this, or in order to get in terms of partial pressures, we have to divide it by RT, of course, and we're going to subtract the total pressure, also divided by RT. And we're going to put our Moore flux in terms of that, but we also, again, still need our mass transfer coefficient. I should have put that over there, but whatever, we'll just put at the end. So anyway, knowing this equation, and now that we put the Moore flux in terms of partial pressures, we're actually going to now just solve for this differential, because we have the change in Moore, what am I trying to say? We have the change in Moore concentration, and we have the change in position over here. So if we just divide the change in Moore concentration by the change in position and just manipulate some variables, since we know that none of these three things, the cross-sectional area, the gaseous flow, and the molecular weight, none of those are going to change. So we can just put those over there, divide it over, and we get our answer. So we are going to do the Moore, the change in Moore concentration of this gas divided by the position is equal to, it would be the NW, as we just made here, the Moore flux of the water, multiplied by, of course, our specific area, oh yeah, these cancel out, sorry. Let me look at what cancels out really quick before I keep going, because I have a specific area. Okay, this would cancel out. NW encapsulates all that. So we're using our flow rate, which we're dividing by, and multiplied by molecular weight. So that would actually be Moore flux times the specific area multiplied by the molecular weight, and that is all over our beautiful gaseous flow rate. But there is one thing I have not mentioned yet. So we talked about the position being, or increasing downwards in this tube, right? This is where it's going to come into play. So since it's increasing downwards, when our gas concentration, as it goes upwards in the tube, it's actually going to increase our water, our gas concentration of water is going to increase, because this air is going to hit more water and it's going to have more of a concentration of water in it. So as it goes up the tube, it increases, meaning as it goes down the tube, it decreases. So we need this to make this negative. And that gives us the differential of the Moore gas concentration in respect to position. So moving on, I'm going to just fold this more. So moving on to the second part here, we know that, before we're just gonna, I just want to define what we're looking for. So we're looking for the change in temperature of the water in respect to position in this tube too. So what we're going to do to start off here is we're going to know, or take what we know about the enthalpy of the liquid in the system, and we are going to create a differential equation through setting the enthalpy of the liquid, like two different terms that we know on the left. So, okay, sorry. Let me just say this again. We know that the enthalpy of the liquid, in terms of two different, like in terms of mass and heat transfer, and in terms of the scenarios in this tube. So we're going to set those equal and then create a differential through them, because we know that temperature encompasses enthalpy. So enthalpy encompasses temperature. Sorry. So we know that in this scenario, we need the cross-sectional area of this tube, the liquid flow rate if we're going to have the temperature of the water because it's going to be liquid running through, and we're also going to have the specific heat of the liquid and the change in temperature of the liquid, of course, too, if we're trying to solve for the change in temperature in respect to position. So now we're going to look at the enthalpy in respect to position in this tube, which would, of course, if we're using enthalpy, we need to use the heat transfer coefficient. We're going to multiply this by the change in, or not change temperature, by the, oh yeah, no, it is the change in temperature between the gas and the liquids, and then multiply that by, of course, our specific area in this stuffed region of this tube, and then multiply that by our mass transfer coefficient in respects to position. Very similar to what we did in the first part, but instead of concentration on the right side, it's going to be temperature, and since we have it in terms of temperature, we also need to add our heat transfer coefficient. Sorry, can you see? Yes, you can. Okay. All right. So going forward from that, we already have, oh wait, I also didn't add the second part of this. Since we have liquid vaporizing, we actually, I can't believe I forgot about the vaporization part, sorry. So since we have liquid vaporizing, we know that we need to, on the right side where we're getting our heat transfers and mass transfers, we're going to have a heat and mass transfer also while the water is vaporizing upwards in this tube through the air moving upwards. So through that, we know that we have the heat of vaporization multiplied by the molar flux of this water, and then also that's going to be multiplied by the specific area where it's encapsulated, or no, not where it's encapsulated, the whole thing's encapsulated, where it is stuffed, and it's corn tube stuffed, and then also multiply that by our mass transfer coefficient, Kc. While also having this in respect to position. So, because this whole thing needs to be in respect to position on this side, because that's we are defining all these things that are happening within this tube, which has the position. So anyway, moving forward on that, we know that we have on this side this equation in respect to position, and this in respect to position. So if we just divide that over, we can put the change in temperature of liquid over the change in position. So we're just going to manipulate this equation really quick and get our final answers. So the first thing we want to know is if we divide, since we're trying to isolate this change in temperature, if we divide this cross-sectional area over, we're going to just have the area, or we're dividing the area of that spot by the cross-sectional area, so we're just going to be left with a lowercase a, because we're dividing on the denominator, if that makes sense. So, wait, denominator. Yeah, on the denominator. Okay, yeah, so pretty much we're going to have Kc and Kc cancel out because we have them just subtracting one another on this side. Heat of vaporization will stay, more flux will stay. I think that that's it. We just are going to manipulate this area since we have a volume and we have an area. So anyway, we are going to do change in temperature. Liquid, can you still see? Yes, okay, you can. Change temperature of the liquid over the change in respect to the change in position, and that is going to be equal to our, since we have A, we're going to send out over, yeah, okay, over our liquid flow rate times the specific heat of the water. Sorry, I'm just confusing myself with all these variables right now. And then that's also just going to be multiplied by what we have over here. Over here, the heat transfer coefficient, subtracted by the temperature of the gas minus the temperature of the liquid. And that will be subtracted by the heat of vaporization times the molar flux of the water. Giving us our final answers. Sorry, I got really confused with the algebra with our areas, but this is correct for our differential in respects to the temperature of the liquid in this tube in respects to position. So now we're going to do one more part. I'm going to just roll this up really quick so I can get back to our beautiful picture here. So the last one we're going to do is the change in temperature of the gas. Oh my gosh, I can't talk right now. The change in temperature of the gas in respects to the position of this in this tube. So it's going to be very similar to what we just did, but instead we actually need to first look at this tube. So like part of this tube. So we know that this is a closed tube. Okay, sorry, I shouldn't say part of this tube. We're gonna look at this tube and what we know about it. So one thing we know about this tube is that it is a closed tube. So the enthalpy, what we know about the enthalpy in a closed tube is that it's remains constant. Sorry, there's no enthalpy change in that tube. So knowing this, we know that the change in enthalpy of the liquid minus change in enthalpy of the gas is going to equal 0, which also means that the enthalpy of the liquid is equal to the enthalpy of the gas. Well, using that, we can create a system of equations that will allow us to find or solve this differential. So going forward into that, we need to define what the enthalpy of the gas is in this system. So first off, we know that we need our area, cross-sectional area, our gas flow rate, our temperature of our gas, and oh wait, change in temperature of the gas probably. Oh wait, no, it's changing all these. My bad. I'm just gonna do this. Change in all of these because I don't know what I'm doing. Okay, so we're gonna find the change in cross-sectional area. The reason I forgot that is because there's no change in cross-sectional area, flow rate of the gas. Oh, and I also forgot I need the specific heat of the gas here too. Okay, and that will actually be added to, we have this vaporization going on still, right? So we need the vaporization within the cross-sectional area multiplied by the flow rate of the gas and the molar concentration of the gas, and this is going to be divided by the molecular weight. So really we just need the heat vaporization, the flow rate of the gas, and the molar concentration of the gas, just like we did in part 1. Or not part 1, just like we did in the solving the first differential, but we want to multiply it by the cross-sectional area over the molecular weight just for unit purposes. So moving forward there, that's the left side of the equation. When you set this equal to the heat transfer coefficient, just like we did earlier in part 2, multiplied by the good old temperature of the gas minus the temperature of the liquid, and then this is also going to be multiplied by the mass transfer coefficient, and then, oh wait, actually we don't need the mass transfer coefficient here, I do not believe. No, we don't need that, my bad. But this is going to be multiplied by the specific area in the cross-sectional area in respects to the position, subtracted by the, again, heat of vaporization, multiplied by the molar flux of the water, multiplied by, again, our area of the stuffed part. I believe that's what we did in part 2. Yeah. Oh, yeah, actually, so we will have the mass transfer coefficient in each of these, but they're actually just going to end up canceling out. So we can just cancel them out immediately, but I mean, they are there, they're supposed to exist, and then in respect to our position. Okay, so moving on from there, we're going to manipulate this equation a little bit because we know, first of all, that we have the change in all of these things. Well, what is actually changing here on this side? Not the cross-sectional area, not the gaseous flow rate, not the temperature. Oh wait, no, not the not the heat capacity, not heat capacity, specific heat of this gas, not the heat of vaporization area again, gaseous flow rate again, and molecular weight. But we are looking for the change in the temperature of the gas, and that will change as the position is changing. And we're also going to have a change in this molar concentration as we saw earlier. So let's just go ahead and take out all the things from this, like if we're looking at respect to change, because they aren't changing. So we're gonna take out the, okay, you can still see barely. I don't know what to do here. Okay, you can still see, so I'm gonna do just this line, then we'll see where we go from there. So the area times the gas flow rate times the heat, no, I keep saying heat capacity, the specific heat of the gas, and this is multiplied by the change in that's multiplied by the change in temperature, the gas divided by dz, because we can just cross out the dz's over here and divide them over, and then this is added to the good old heat capacity. Heat capacity. I keep saying heat capacity. My bad. That is added to the heat of vaporization, multiplied by the cross-sectional area, multiplied by the molar flow rate of the gas, divided by this molecular weight, and multiplied by the change in concentration of the gas, respective position. This side's just going to remain the same, so I'm just going to write this down really quick. Our A's, I think, will go ahead and cancel out, though, with our areas. Well, I'm going to wait to do that just because we have our A's over here, too. All right, I think it's our A's. Yeah, I'm just going to write this out. I'll simplify it a little bit. I'm confusing myself. Okay. And that's it for now. Okay, so now I'm just going to simplify this equation. And one way I can simplify this equation is I need to go and figure out what this change in molar concentration in respect to position is, which we know from part 1 since we solved it. So let's go back there and see what we got. It is the, I don't know if you can see this. Yeah, you can, okay. Negative molar flux of water multiplied by the specific area, multiplied by the molecular weight, divided by the gas flow rate. And what I'm going to do is I'm actually going to rip this part out because that will help us simplify this. So, knowing this, oh my gosh, having problems. Knowing this, we can cancel out. So we have our A, oh wait, it's over here. A, G, so our G's will cancel out. And our dy dz, So we'll have negative NW. Okay. And our m's will cancel out, is what I was trying to say. Okay, cool. So that gives us a, I'm just going to write this down really quick because we already just went over all of this, what this means. PG, DZ. And then this is multiplied by the negative NW, which is more flux of water, multiplied by the specific area. Okay, I need to move this upwards, so I'm going to just do this. Okay, so that's what we've got so far, and this is equal to the side of the equation, which I'm just going to write like that. Well, one thing we do know is we have A in every single spot, so we can cancel those out. Should do some basic algebra. I'm not going to run you through this actually. I'm just going to go ahead and write down, we know that this is the gaseous flow rate times the specific heat. No, my gosh, not specific heat. Oh yeah, no, it is. Specific heat of the gas times the good old temperature. This is what we're looking for. We're going to cancel those out too because we're going to divide this all over. So really what we're going to do, we're going to subtract this over right now. And by subtracting that over, we're going to actually get these to cancel out, these A's to cancel out, which we already got. And the more flux, yeah, no, it does. It also cancels out. And yeah, that's actually it. So what we're going to do is we're going to divide these over. So I'm not just going to cross those out. And we are just through algebra, just going to do the change in temperature of this gas with respect to position is equal to the specific area times this heat transfer coefficient divided by the gaseous flow rate, because we're going to have that still over here on this side. When we divide that over, it's going to be in the bottom, multiplied by our specific heat, because we just had to divide both of those over, multiplied by the temperature change of the gas and the liquid. And that is going to be all of it as we cancel all these out. Sorry, my algebra was really bad today, so it took a little long, but that would be our final answer for the differential of the change in temperature of this gas in respect to position. Thank you very much. I hope you enjoyed this video, and I am going to start part 2 in a second.